Small correction, it's Davis with an S.
Sorry.
No problem. So yeah, as you said, I've been working at Conviva for about a year now. I've been working heavily in their usage of Spark for about the past 6 months. And I'm here to sort of talk about one of the key problems that we solve with Spark and are currently, or just recently sort of are getting results on, we're really excited about. All right, how was that? Good? Okay. All right, so just high level, going to tell you who we are as a company, what was sort of the key problem we needed to solve. Again, this is probably looking familiar at this point. How that led us to the usage of Spark, and what we're sort of planning to do with Spark in the future. So to start with, just a little bit of a context. Quality has a huge impact on user engagement in online video. This is a snippet from a viewer experience report we published earlier this year. And as you can see, even the moderate increase in terms of the time you spend buffering relative to the total time you spend playing has a huge impact on how long the user is actually going to stay engaged and continue watching. So I hope that this is a compelling point for why it's important to sort of provide high quality online video, as more and more traffic is eventually moving to the web. And it's the core reason behind what we do, which is we optimize end user online video experience. Key things like quality, start time, reduce the time you spend buffering, all those sorts of things. And we do that a couple different ways. So we provide key historical real-time and offline metrics for online video providers and distributors. We help them maximize their quality by providing adaptive bitrate algorithms, helping them do content distribution network switching, and additionally, do sort of detailed traffic shaping between CDNs, because they might have certain pricing contracts set up with various CDNs, and they obviously want to send traffic where it doesn't cost them the most. As a result of providing all these services, we get to see a really diverse swath of traffic from the online video ecosystem. Mostly premium content providers like HBO Go, ESPN, BSkyB, CNTV, as well as user-generated sites like Vimeo and Ustream. We get to see data from live events, long-form VOD, short-form VOD, and additionally, we get to see traffic across all the major CDNs, including ISP CDNs like Verizon and AT&T, in addition to the Akamai's and the level 3s. Now, from all of this data that we've gathered, there's sort of one core truth, and that's that video delivery over the internet is hard. It's very difficult to get it right. And a fundamental sort of core issue to that problem is that there's a big disconnect between the viewers and those who are publishing content on the web. A viewer might see their video, they might be watching their favorite stream, 30 seconds in, it starts buffering. They don't know why. They're upset. They rage. And in this rage, they might call the provider, right, who sees, they have this complex sort of upstream, encoding system. They eventually deliver it out to a content management service. They host it and eventually publish it out onto a CDN. And from there, they're oftentimes flying blind. They don't see how it's performing. So when this user's calling in upset, they have no idea where in their pipeline things are going wrong. And we sort of help complete that loop. We sort of let them know where in the pipeline things are going wrong, how to fix it, how to improve it. Now, once they've ironed out these problems with their delivery stream and they're sort of reliably publishing things out on their CDN, there's still problems, because the problem is a single CDN is simply not sufficient to deliver high quality video over the web everywhere. This was some data taken from a SIGCOMM paper we published last year from the top 3 CDNs across 6 major cities. Here we have the amount of time spent buffering relative to total viewing time across these top 6 cities, and it's all over the place. No single CDN can perform well everywhere. That's what we've seen. This is sort of fundamental. In addition to that, you can't just fix this by sort of providing a static policy because CDN performance varies over time. All 3 major CDNs across the same time interval suffered major performance degradation. So this is a serious problem, and it's sort of the core problem that we were aiming to solve. Because fundamentally, where there's heterogeneity, there's room for optimization. So at the core of this, for each viewer, we want to decide what CDN they want to stream from. But it's difficult to model the entire internet. That's a bit out of scope, unfortunately, and things can change rapidly. So we want to make this decision based on the real-time data that we're collecting. So I'll give you some, just to drive this sort of insight home with a simple example. For each CDN, we will partition the clients by city, and for each of these partitions, we'll compute the buffering ratio that we see in each, right? And imagine we have 2 CDNs across these 5 major cities. And you can imagine these are sort of just heat maps, universal coloring scheme, green good, red is bad. And each one of these cells sort of represents the average buffering ratio in each one of these regions or cities. And then from there, for each one of these regions, we select the best CDN and send clients to this CDN. So in this particular region, in San Francisco, CDN1 performing terribly, while CDN2 performs great. So the clear option is to send clients to CDN2 instead of CDN1 in San Francisco. And we can repeat this process for all regions until we end up with sort of this optimal performance across all cities. This is sort of the core of our idea. But again, as I said before, this can't be solved with just like a static policy. You can't compute this offline and then just apply this as a policy. It needs to update continuously, because if there are changes in performance, we need to change the decisions that we make, right? We need to constantly be making sort of updating about what the feedback is, because performance is not consistent over time. So in summary, we need a coordination system that's implementing this optimization algorithm that dynamically selects a CDN for each client based on the individual client, some set of attributes that we collect from them, aggregate statistics that we've seen over the recent sort of time window. And again, this needs to be merged with these sort of content owner policies. They are concerned about how much traffic goes where because it costs them real money. It might be a 4x more expensive to send traffic on one CDN than the other. And all of this needs to be based on real-time data. So this brings us to the question of which processing framework do we use. This is a big problem to solve. We'd considered Twitter Storm. One of the core issues with this, though, for us was that fault tolerance model affects accuracy. By replaying these messages later, you could introduce skew to your sort of data detection or your calculation of these offline statistics and potentially adversely affect the decisions that you're making. In addition to that, it's a non-deterministic streaming model, which frankly is just sort of unpleasant to work with these sorts of problems, especially if things go wrong. We considered rolling our own. We already have a bespoke metrics processing live streaming stack that we built, but frankly, to sort of build this out to do even more complex ML algorithms was too complex. There was really no need to reinvent the wheel, given that Spark was sort of starting to show its head. And the really nice thing about this was it easily integrated with our existing Hadoop architecture. It was really painless to start pulling data, off of piggybacking this on top of the existing architecture we had. The flexible, simple data model was really easy to work with, and fundamentally, writing map is generally easier than writing update, and that was sort of really appealing to us. So, basic architecture: we have a Spark cluster that's pulling data from our current live streaming stack. It computes these performance metrics, computes these tables inside the Spark cluster, which is relayed to a storage layer. And this is eventually pushed out to our decision makers, which are able to make constant time, sub-millisecond decisions back out to the clients about sort of where to route traffic. So some results. So this is sort of a plot of some of our top customers, or a subset of our customers, about how they perform, relative to the number of views that are actually out there, not buffering, doing well in terms of average bit rate. And by applying the system to one of our mid-pack customers, we were able to elevate them to one of our top performers. So this is a really exciting initial result for this system. So Spark's role in all of this. Key to this was that Spark development was rapid. It was very easy to sort of build this quickly. Aided both by its excellent programming interface and highly active community. I'm sure many of you have had questions answered late at night by maybe Matei or somebody. But yeah, I mean, it's really exciting to work with the Spark community. It's been really helpful. The interface was incredibly expressive. We were able to develop this complex online ML decision-based algorithm in about 1,000 lines of code. And it was, as a result, very easy to sort of prototype these algorithms and develop as we were working along. It also made scalability a far more manageable problem, right? We saw the CDN heterogeneity, and we could approach it in the mindset of what sort of algorithms are we going to use, how are we going to solve this problem, and not how are we going to compute all the data in time. And after initial teething problems, we've been running this sort of system reliably in a production environment for several months. But it wasn't all smooth sailing. There were some problems, especially in the early versions. There were lots of silent crashes, which were sort of hard to deal with. And they were often difficult to debug, requiring some tribal knowledge, hence the late night questions. But again, the community sort of helped us work through this. Difficult configuration parameters, oftentimes the inexplicable results. This has been massively improved in the more recent versions, so that's very encouraging. But the key thing I think that we learned is that it requires a fundamental understanding of the underlying data model to write effective reliable, stable Spark programs. Understanding how lineages grow, understanding when computation happens, understanding how sort of the failure model works is really essential to writing these, right? It's very easy to get lulled into this very simple interface and how quick and easy it is to write these programs. But in order to do it effectively and at scale, you really need to understand what's going on under the hood. And I think that's a really important point. Now, this was great. We worked through these problems. We had the system running. But there was sort of an additional constraint that had to be added. And that was literally constraints that our customers put on us, right? As I mentioned earlier, these CDN pricing policies, we might be optimizing traffic, but we might also be costing them 4 times as much. So, they might say to us, well, hey, you're improving my buffering ratio by, a little bit by sending it to a bunch of traffic here to this other CDN, but, this is also costing me an arm and a leg. So how do we had to figure out how then do we enforce these constraints in the optimization. So the intuition is you can imagine a process where we have these 2 sort of performance heat maps, and we want a 50-50 split across these 2 CDNs. So you can imagine that an initial sort of reaction might be, okay, we're performing poorly in this region on CDN2, so let's send, or on CDN1, so let's send clients to CDN2 instead of CDN1. But now we're violating constraints. So we send a client in another region where CDN2 is performing poorly, and we send them back to CDN1. Right, instead of CDN2. And you can imagine repeating this process of swapping clients until you've reached sort of an optimal mapping between clients and CDNs. And the net result is you end up with sort of this constrained, optimal output, whereby you didn't have enough clients. This particular region was so heavily populated in clients, there weren't enough to send back, so you were only able to send a subset to CDN2 to give them the optimal performance. So we can still optimize in lieu of these constraints. As it turns out, this sort of problem can be framed very nicely in a linear program, or more precisely, an integer program. The problem, though, is that in order to sort of reach this optimal mapping, we have to see the set of requests that are being made, if we were to do this in the traditional sense. And obviously, we can't wait for 1,000 or 2,000 requests to accumulate before we compute this LP and then send back a batch of responses. People are going to be waiting 30 seconds for the videos to start while we figure things out. But it turns out that you can parameterize an approximate solution to this problem by computing an LP on data you've seen in the past. I won't get into the nitty-gritty details about the math involved, but if anyone has any questions afterwards, I'd be more than happy to talk to you about it. But the net is then we needed to compute an LP on real-time data, and in fact, multiple LPs, so hopefully we can compute them in parallel. And Spark supported it, right? It wasn't all of a sudden we had this new requirement, we had to rethink everything. It was a matter of simply just writing the code and shipping it out. As long as we have the native libraries and the Spark nodes themselves, we're good to go. And currently, we're running it on, in trials, we ran it on 20 LPs, each with 4,000 decision variables and 350 constraints here, give or take. And they're all computed in parallel in about 5 seconds. And this is on data that's chunked at about a minute. Now, in addition to all these requirements, we built the system out, but tuning was an incredibly important part of this, right? We can't just select a CDN based on a single metric, right? If we're picking it just on buffering ratio, and the result is that we're sending it to a CDN where everybody's failing to join, that's not going to really, behave terribly well. People are going to be very upset. It's going to generate poor quality. So we need to figure out what sort of utility functions best predict sort of engagement. In addition, the confidence in the decisions we have depends on how much data we've collected. So this depends on what sort of time window we're looking at, what attributes we're using to separate the data out. And finding these things out and tuning the algorithm as we're going along needs to happen quickly, right? We can't wait for production trials to happen while we're sort of figuring out and tuning and improving this algorithm. So we need to be able to validate these changes quickly, which means simulation of an offline algorithm was truly essential. And this led us to build our simulator system, which essentially reuses about 90% of the code we wrote for the production system with an extra 10% to build sort of just the harness to replay the data faster than real time, essentially, and then an extra layer to do evaluation. So this essentially loads production traces with randomized initial decisions from our HDFS cluster. We generate the decision table with an artificial delay, so we're sort of trying to simulate what the traditional feedback path would look like. We produce simulated decisions, again, on the Spark cluster, and then collect all this data to do evaluation, again, all in the Spark cluster and all iteratively. So eventually, sort of the future of Spark at Conviva, we want to leverage more of the Spark streaming API. When we first built this system, Spark streaming didn't exist yet. So we sort of rolled our own. So we're really looking forward to sort of benefiting from all the extra instrumenting APIs and optimizations that come with Spark streaming. Now, as I mentioned before, we have this bespoke live streaming stack, as well as a traditional Hadoop offline processing stack. And we want to sort of unify this together because it's a headache managing these two systems. And this will essentially lead us to develop a processing platform where we can have, again, sort of this partially aggregated common data input whereby we can build all sorts of processing apps around it, whether it be an anomaly detection system, customer-tailored reporting, all in addition to this optimization program. So in summary, Spark was able to support our initial requirements for fast, fault-tolerant, performance-oriented computation for an online decision maker. New complexities like LP calculation just worked in the existing architecture. It was fantastic. And Spark has become an essential tool in our software stack and has become more so in the future. And it's truly really exciting. So I just want to say thank you to the Spark team, to Henry, who's been a huge help as a consultant. And I just want to thank you guys. Spark has been an excellent software platform, and it's been a joy to work with. Thank you guys for listening. Are there any questions?
Wait, we'll start with this one.
Great talk. Thanks for the detailed discussion. I have a question that is probably juxtaposing the two talks I heard just, Conviva and the one before this. So both use time series data. I didn't quite get a sense with Conviva what input format or underlying storage you were using. But the question I wanted to ask both the presenters was how much did the choice of the underlying storage and the input format you used made to your use of Spark? And particularly in context of, are you actually doing the work that Spark is otherwise supposed to do in terms of distributing the workload and maybe caching some of this to the input format and the underlying storage?
The input storage itself wasn't a huge deciding factor. I think the primary choice for us, we sort of accepted the fact that we might have to build a bit of a translation layer if necessary. But given that we were heavily embedded in the Hadoop world, it really wasn't painless at all. I think more for us, the decision came in terms of the processing model itself. All these other sort of live streaming systems, go for sort of this, the Atmos one sort of at record at a time thing, and the batching processing model was sort of really what drew us to this because it's so flexible, right? We could do all sorts of these wacky things like computing these regression problems and then simultaneously computing LPs, right? With something like Twitter Storm, you'd have to build. So at the time, Twitter didn't have sort of the extra layer that they have now for sort of doing batching. So essentially, doing something like LP calculation was sort of out of the picture.
I'm curious if you could elaborate a little on your comment about sort of not being seduced by the very, very simple API, and you have to kind of understand how the guts actually work, because I think a lot of technologies, especially in distributed computing, sort of have that characteristic. It's low ramp to your first running code. And then all of a sudden you discover that there's a whole bunch of magic going on that you need to have some insight into. If you could expand on that just a little bit.
So I think sort of the best way I can explain it is sort of two key examples. So we started running into a problem with our streaming system where lineage chains, this is before Spark streaming was around, so we were sort of building this on the fly. We ran into this actually in our simulator stack where all of a sudden these lineage chains would grow to an absurd number, right? Because essentially we're using the previous RDD to do this iterative calculation, right? So we ended up with a lineage chain that was like thousands of nodes long, right? And all of a sudden these computations are grinding to a halt, right? And sort of figuring out that, it's like instead of, by avoiding this checkpointing thing and just reading straight from memory to do the next computation, sure, that sounds fast, but the problem is we didn't realize we were, incurring this extra cost. So understanding, how these lineage chains are generated and when they're cut is incredibly important, right? Because it's, the immediate intuition is like, oh, I'll just read everything from memory. But the problem is you keep building these lineage chains and they're expensive, especially when you fail, right? If you have a lineage change that's 1,000 translations long and then something fails, like recovery is going to essentially, not going to happen. It's just going to be way too late. Another thing we ran into was generation of shuffle files at, a rather absurd rate because of some underlying process that we were doing. So realizing when those are generated and how they're generated and how to deal with sort of cleanup associated with those was also sort of a key challenge we faced. So, I mean, those are sort of two key examples I can point out about, when understanding the underlying system really helps you.
I actually had a question for both presenters. How do you guys decide to scale Spark? I know it's memory heavy, so do you look at the memory usage, decide to add a node, or do you look at CPU? What do you guys do?
So that's actually an interesting question. We're running, I think I missed this point. So our current production cluster computes about 2 million sessions per day chunked at 1 minute, and the computation takes between 6 and 15 seconds, and that's on a 4-node cluster. Now each one of these nodes are pretty fat. They're like 200 gigs each, 64 cores. But even though it's 4 nodes and though they're fat, we're hilariously over provisioned. It's running through very, very quickly. And I think the key thing to understand when you're sort of deciding to scale things out is frankly scalability testing, right? You have to run it. You have to figure out where your bottlenecks are and then decide where to grow. And so instrumenting Spark, which is actually sort of the new feature that's coming out now, we haven't quite yet implemented all that, is going to be an important factor in that, in deciding how we essentially scale out our cluster.
All right, last question.
So are you having to deal with JVM heap management? How do you manage those 200
we actually haven't run into JVM problems. Like I said, we're hilariously over provisioned at this point. I think we did, so a key thing is actually Spark cleanup really helps manage garbage collection, right? If you're really good, essentially just allowing things to build in the cache until you have to evict them, especially when you have 100 gigs allocated on a machine, we would notice GC pauses of between 15 seconds and a minute. But once we got sort of, when Spark TTL Cleaner came around and we could sort of clean up these shuffle files and, get rid of old RDDs sort of more aggressively, we basically see no full GC.
So do you allocate those Spark processes with a full heap, a full 200 gig, or?
Yeah.
Yeah?
All right, thanks, Davis. And let's give him another round of applause.